For most of the voyage, Alpha Centauri would have been little more than a point of light, visible through the ship's instruments but still separated from everyone aboard by years of travel. Then, slowly it would begin to change. The stars would brighten, their positions would shift, and what had existed for generations as a destination on old maps would finally become a real place outside the ship's windows. People would gather at the ship's observation windows to see it for themselves. Some would have spent their entire lives traveling toward those stars, born aboard the ship and grown up with stories of a world their ancestors had chosen but never expected to see themselves. For the first time, the promise that had carried the settlement across interstellar space would no longer feel distant. They had reached another star system, but reaching it would not mean they were ready to leave the ship. The generation ship would still be moving at enormous speed, and slowing it down could take years rather than days. Its engines, power systems, habitat and life support machinery would all have to survive that final phase of the journey, because the people aboard would still depend on the ship for almost everything while they worked out what life the new system could actually support. What they found would shape every decision that followed. The planets might not follow the orbits predicted centuries earlier. Radiation around the stars could be stronger than expected, while a world that once looked promising from Earth might turn out to have unstable weather, a hostile atmosphere, contaminated soil, or no accessible place where a permanent settlement could safely begin. So the first years near Alpha Centauri would probably involve far more watching than landing. Probes would move ahead of the ship, instruments would study each candidate world, and the settlers would compare what they found with plans written by people who had died generations before. After such a long crossing, that caution might be difficult to accept, but rushing toward the first inviting surface could place the entire settlement at risk. Even a successful landing would only mark the beginning of the settlement. A colony becomes independent when it can survive equipment failures, replace essential machinery, produce what it consumes, and continue without one aging spacecraft carrying most of its tools, knowledge, and industrial capacity. Until then, every settlement on the surface would remain connected to the generation ship above it. The moment another sun fills the windows may feel like the end of the journey. In practice, it would mark the beginning of a slower and more uncertain task, turning a destination into a place where human life could continue without the ship that brought it there. Once the ship reaches another star, the work will move from slowing down and surveying unfamiliar worlds to deciding whether its passengers can build a settlement capable of surviving on its own. If you enjoy exploring questions like this with me, subscribing helps others find the channel, while liking and sharing the video helps even more. Now, let's begin. Alpha Centauri sounds like one place on a map. Give a destination a name, and it begins to feel almost owned. But a ship arriving there wouldn't find one bright marker waiting below. It would enter a neighborhood of stars, planets, orbits, dust, radiation, and choices. Alpha Centauri A and Alpha Centauri B form a close pair. Both are stars somewhat like our Sun. Farther away, Proxima Centauri travels through space with them. It's a small red dwarf with planets of its own. Alpha Centauri A, B, and Proxima belong to one real stellar system. That changes how you plan an arrival. A family moving to a new city doesn't study one house and ignore everything nearby. They check roads, water, hospitals, and somewhere to stay if the first address falls through. An interstellar mission needs the same kind of map, stretched across an entire star system. Proxima B is the strongest known candidate for something resembling a destination. It's roughly Earth-sized. It also circles within the region where liquid water could exist if other conditions are right. Those facts make it important. They don't make it another Earth. We still don't know enough about its surface. We don't know whether it has a substantial atmosphere or what that atmosphere contains. We don't know whether reachable water is there. Even the term habitable zone describes only how much energy a planet may receive. It doesn't certify the planet as habitable. This is partial knowledge, not ignorance. Astronomers found Proxima b by measuring the small pull it exerts on its star. That gives us strong evidence that the planet exists. It also gives clues about the planet's orbit and minimum mass, but those measurements can't tell us whether people could stand there, build there, or survive there. So the route map can't end with one line pointing at Proxima b. It needs branches and fallback options. Alpha Centauri A and B may have worlds that remain difficult to detect. Other planets or moons could offer resources, safer orbits, or temporary shelter. Stations might operate in open space before anyone risks a landing. Even an empty orbit could become valuable if it offers stable conditions and access to several possible worlds. Choosing one blue planet in advance would feel simpler. People love place names because a name makes uncertainty feel smaller. It turns a complicated system into something that sounds settled. Real planning has to resist that comfort. Every confirmed object changes the map, and every missing measurement leaves more than one sensible route. Arrival turns wonder into responsibility. The destination is the whole Alpha Centauri system, not one imagined patch of ground. Proxima b is one promising address inside that system. The first map must leave room for every option the evidence still allows. On the briefing table, Proxima b already has 2 numbers beside its name. Its minimum mass is about 1.3 times Earth's, and it circles its star at roughly 0.05 astronomical units. That distance is about 4.6 million miles, or 7.5 million kilometers. It sounds terribly close. Around a small, faint red dwarf, though, that orbit receives enough starlight to place the planet in what astronomers call the habitable zone. That label can be encouraging. It can also make us invent everything else. The habitable zone is a filter based on incoming energy or flux. It marks the range where liquid water might exist under suitable conditions. It doesn't tell us whether water is actually there. It doesn't reveal the air, the surface pressure, or the chemistry. It certainly doesn't certify a place for people. You can think of it like checking the wattage on a lamp. The number tells you how much energy reaches the table. It doesn't tell you what's sitting beneath the light, whether the room has air, or whether the building is safe to enter. The mass measurement has a similar limit. Proxima b was detected through the small pull it exerts on its star. That method gives us a minimum mass, not a complete description of the planet. A world near 1.3 Earth masses could be rocky, but the number alone doesn't show us its surface, its atmosphere, or what materials are available there. So the evidence has done something important. It has moved Proxima b from a hopeful idea to a real world with a measured orbit and a constrained mass. Alpha Centauri is no longer just the nearest stellar system with attractive possibilities. It contains at least one confirmed planet in an orbit where the energy balance deserves close attention. But the empty spaces on the briefing table still carry most of the life support decision. Atmosphere, blank. Surface pressure, blank. Water and chemistry, blank. Those aren't minor details waiting to be filled in after we choose the landing site. They decide whether people could live on the surface at all. This is the difference between detecting a planet and proving a home. Detection narrows the range of possibilities. It gives a mission somewhere real to investigate. It doesn't give planners the confidence to promise breathable air, usable water, or a surface settlement. Proxima b may become a colony site, an observation target, or a world approached only by machines. The measurements we have cannot choose among those futures. For now, they justify sending better instruments and keeping several plans alive. A real address is valuable. It still isn't permission to move in just yet. A journey to another star should never depend on one promising dot. We don't plan a family road trip that way, and this trip would carry a civilization's future. One closed road could ruin everything. Alpha Centauri gives planners something better than a single destination. It gives them a system. Proxima Centauri has a confirmed planet in roughly the right temperature range. Around Alpha Centauri A and B, searches have also placed strong limits on where large planets can hide. Astronomers still debate smaller possible worlds there. The evidence changes as instruments improve. That uncertainty belongs on the system chart. It isn't an embarrassing blank. It tells the ship what to survey first, which routes to keep open, and where to hold reserves. A doubtful signal may deserve a close look. A stable orbit with no known planet may still contain useful rock, ice, or dust. Even an empty region can offer a safer place to wait while instruments study something more dangerous. A ship, therefore, plans for several roles inside one system. One body might be the scientific target, another might supply water, a small moon or asteroid could provide raw material, a distant orbit could serve as a sheltered assembly point, robotic probes might visit the most uncertain worlds while the crew remains far away. This is how optionality turns astronomy into survival. The ship doesn't need every place to be comfortable. It needs several places to be useful. If the leading planet has a hostile atmosphere, the mission can remain in orbit. If its surface proves unstable, machines can descend instead. If the planet offers nothing usable, nearby rocks may still support repairs and fuel production. The same logic protects the people who come later. A settlement needs supplies, power, communications, and room for equipment failures. Those jobs don't have to happen on the same world. In fact, forcing them onto one world would create a single point of failure on an absurd scale. Alpha Centauri is a real anchor because we have measured stars, mapped their motion, and confirmed at least one planet there. Yet those measurements don't settle the questions a settlement would ask. They don't reveal every atmosphere, surface, resource, or safe orbit. Much of the system would still need to be surveyed after arrival. So the plan should arrive with branches, not a verdict. Keep alternate orbits available. Keep nearby rocks in play. Protect fuel and equipment for a fallback site. The most attractive world may earn the first careful approach, but it shouldn't receive the mission's whole future before the evidence arrives. Because the best world in the system can still punish haste. What might that promising target be hiding? Proxima b has earned its place at the top of the list. It's close to Earth's mass, and it circles within the region where liquid water could exist. Better still, it orbits the nearest star beyond our Sun. If you were choosing one distant planet worth crossing interstellar space to inspect, this would be the obvious candidate. And of course people want it to be the answer. After such a long flight, a dark world with familiar gravity and possible water sounds almost generous. It might offer solid ground, useful minerals, and temperatures that allow more than sealed machinery. It could even have an atmosphere. We don't know yet. That uncertainty doesn't make Proxima b a false lead. It makes the planet worth the mission. The same basic measurements that place it in the habitable zone give us a serious reason to go. They just can't tell us what conditions are like on the ground. The trouble begins with its star. Proxima Centauri is a red dwarf, much smaller and dimmer than the Sun. For the planet to receive enough warmth, it must orbit very close. 1 year there lasts about 11 Earth days. That tight orbit places the planet beside a star that can be far more violent than its gentle red glow suggests. Proxima produces powerful flares. It also exposes the planet to stronger X-rays and extreme ultraviolet light than Earth receives from the Sun. Those forms of radiation heat the upper atmosphere. Over time, energized gas can escape into space, especially if the planet lacks a strong magnetic field. But we can't simply declare the atmosphere gone. Its survival depends on how much air the planet began with, what gases it contains, whether volcanoes replace lost material, and how well any magnetic field shields it. A thick atmosphere might endure. A thin one might have been stripped badly. Both remain possible. The close orbit may also have slowed the planet's rotation. One side could face the star for long periods, perhaps permanently, while the other remains dark. If so, local conditions could differ sharply. The bright side might be scorched. The dark side might trap water as ice. Between them, winds could carry heat into a milder band. Even that outcome depends on the atmosphere. Thick air could spread warmth around the planet. Oceans might help. Without them, the temperature gap could become severe. So Proxima b deserves both hope and caution. It may be the best nearby world we know, and it may demand shelters, radiation protection, and carefully chosen landing sites. The promise and the danger come from the same place, a small planet orbiting very close to an active star. Possible water earns Proxima b a place on the mission list. It does not make the surface safe. The planet sits close enough to its red dwarf that every burst from the star arrives with very little room to spread out. Estimates suggest Proxima b receives about 30 times the extreme ultraviolet radiation Earth gets. Its X-ray exposure may be roughly 250 times greater. 30 times the extreme ultraviolet, 250 times the X-rays. Those figures don't describe a constant blast everywhere, every day. They describe a harsh radiation environment around a star known to flare, sometimes with little warning for anything waiting below. You know what a bad sunburn does to skin? Higher energy radiation can reach deeper, damage cells and break apart molecules in the upper atmosphere. Over long periods, those particles and photons may help carry atmospheric gases away. But we don't know how much air Proxima b began with, how quickly it loses that air, or whether volcanic activity could replace some of it. A strong magnetic field might offer protection, though we don't know whether the planet has one. So the radiation problem changes the shape of the first arrival. Settlers would not simply choose a pleasant temperature and build on open ground. They would look for thick rock, deep soil, caves or water that could absorb radiation before it reached their bodies. Living quarters might sit underground. Surface work could be timed between bursts, with instruments watching the star for warning. Even a short trip outside could depend on the latest reading from orbit. The landing site would count too. If one side always faces Proxima Centauri, radiation and weather may differ greatly across the planet. A sheltered region near the boundary between day and night could offer better temperatures, yet still face charged particles and sudden flares. The safest place for liquid water may not be the safest place for a person. And that affects who descends first. Machines can take radiation doses that would be reckless for a human crew. Robotic scouts could measure the surface, test the ground, search for caves, and watch several flare cycles before anyone opens a hatch. The first people down might be engineers and medical specialists, not explorers strolling toward a distant ridge. A mission badge offers no protection from repeated stellar flares. Proxima b may still support an atmosphere, water, and protected life. It may even offer places where people could live with enough shielding, but its promise would dictate the settlement. Machines first, humans later, and most daily life beneath a protective layer of the planet itself. People love a planetary average until they have to choose an address. A world can look acceptable in a table and still contain places that differ as much as a desert, an ocean, and Antarctica. Proxima b may make that problem unusually sharp. It receives enough energy from its star to justify sending the mission. But that same nearby star also produces strong X-rays and extreme ultraviolet light. Those can heat the upper atmosphere and help strip gases away. We don't yet know how much atmosphere the planet has kept, or how well that atmosphere moves heat around. The answer may depend on where you stand. Proxima b is probably locked into synchronous rotation, with one side facing its star for long periods. It could also turn in a near-resonant pattern, rotating slowly while repeating a more complicated cycle. Either way, sunlight may not be shared evenly across the surface. Think of a house with one wall beside a furnace and another pressed against winter glass. The average indoor temperature tells you very little about either room. Air circulation decides whether the whole house becomes tolerable, or whether one side bakes while the other freezes. An atmosphere can do something similar on a planet. If it is thick enough, winds may carry heat from the bright hemisphere toward the dark one. Oceans could help as well. If the air is thin, weak, or partly lost, the contrast may become severe. One region might allow liquid water, another could trap ice. A third might be scorched, exposed, or hammered by charged particles during stellar flares. So the useful map isn't one color labeled habitable. It is a climate map broken into zones. The permanent day side, the permanent night side, and the band between them may each demand a different settlement plan. High ground could have less protection, low basins might collect denser air, ice could sit far from the best solar power. A sheltered region could be safer from radiation, yet harder to reach. Hemisphere and atmosphere matter more than one whole planet label. The planet may support a base without supporting travel across its surface. It may offer one narrow belt where machines work outside, while people remain under rock nearby. Even the best location could shift as weather patterns, flare exposure, and atmospheric loss become clearer. That makes the destination both attractive and threatening for the same reason. It is close to an active star. The star supplies warmth, but it also tests every layer protecting the ground. Proxima b isn't one environment. It may be several environments sharing one globe. And before anyone can choose among them, the ship has to arrive slowly enough to stay. So what changes when the spacecraft itself must stop? A spacecraft can reach the right star and still fail to arrive. If it crosses the system too fast to turn, observe, or enter orbit, it has only made a very expensive flyby. Arrival means controllable capture. The ship must lose enough speed for the star, a planet, or its own engines to hold it there. Otherwise, Proxima b flashes past while the crew misses the exit, except the exit is an entire star system. The first danger after cruise is the motion the ship worked so hard to gain. Speed carries kinetic energy. That energy cannot simply disappear when the destination appears ahead. It has to go somewhere. Engines may throw hot exhaust forward. A magnetic sail might push against charged particles. A light sail could use a beam sent from far behind. Whatever the method, fast travel ends with a large braking job. Probe studies have exposed this problem for years. A tiny craft, pushed to a fraction of light speed, could cross the distance within a human lifetime. Yet some of the boldest concepts send it through the target system in hours. The probe may gather valuable data during that pass, but it cannot settle into orbit and study one world for decades. The crossing time makes the headline. Capture decides what the mission can become. For a settlement ship, braking is the first settlement problem. It affects fuel, mass, heat control, shielding, and the shape of the whole vehicle. The faster the ship cruises, the less time passes for people waiting on Earth. Families and institutions may remain connected across a shorter gap. But the ship then carries more energy into every grain of dust. It must also shed far more energy at the other end. Shielding grows harder. Braking equipment grows heavier. The mission may save years in flight, then pay for them in mass and risk. So when we compare possible ships, speed alone doesn't make one better. A slower ship that can enter orbit, choose a safe path and wait for good measurements may be far more capable than a faster ship that cannot stay. Surviving the crossing gets you to the system. Usable arrival begins when speed becomes control. Interstellar mission posters tend to favor the exciting verb, reach. Reach Alpha Centauri in 20 years. Reach another star within a lifetime. The clock stops when the probe passes the destination, which is rather convenient for the poster. A flyby can return valuable science, but it gets only one brief look while racing through the system. A captured probe can slow down, enter a stable path, and keep working. It can revisit planets, watch weather change, map possible landing sites, and relay data for years. If you're planning for settlement, those are very different missions. One probe-scale study shows how severe that difference can become. Its capture-capable case begins with an injection speed of about 4.6% of light speed. That sounds fast, because it is fast. Roughly 8,600 miles per second, or 13,800 kilometers per second. Yet the trip doesn't end when the probe reaches the target system. The outbound flight takes about 95 years. Braking then takes another 46 years. The full path to a useful captured orbit is about 141 years. The exciting headline usually ends too early. That example doesn't set the timetable for a crewed ship. It's a probe-scale calculation built around its own assumptions and equipment. But it exposes the part that fast travel claims often leave outside the frame. Arrival isn't a line on a map. It's a controlled change from crossing interstellar space to operating inside an unfamiliar star system. Going faster may shorten the separation between travelers and people back home. That could preserve more social continuity. Messages still take years, but fewer generations pass before the travelers arrive. The trouble is that every gain in speed raises the cost of stopping. It also makes dust impacts more violent and shielding more demanding. So higher speed buys something real. It may keep the mission closer to the society that launched it, but the same speed must be managed twice. First during the crossing, then again during braking. Put the two mission posters beside each other. One shows a bright probe flashing past a distant sun, able to say it reached another star. The other arrives later, turns, slows, and remains there. Only one can begin learning how we might stay. We tend to want one slider called progress. Push it toward faster, and every problem should shrink. For an interstellar mission that works only until arrival, then the speed that saved decades becomes energy the vehicle must somehow lose. Take the slow case first. A probe crossing at a modest speed spends much longer between stars. That leaves more time for equipment to fail and for Earth to change behind it. Yet braking is less severe. The craft may use a sail, the target star's light, magnetic forces, or a limited supply of fuel. None of those methods is easy. They simply face a smaller task. An intermediate case shifts the burden. The voyage is shorter, so components age less and fewer human generations separate launch from arrival. The mission stays closer to the language, institutions, and aims that sent it. But its arrival system grows heavier. Shielding must handle harder dust strikes. Navigation errors leave less room for correction. Fuel carried for braking adds mass that also had to be accelerated at the start. Then comes the fast case, the one that makes the best headline. It cuts the crossing time sharply. Social continuity improves. Designers may still be alive when their machine reaches the target, but the arrival energy can become punishing. If the probe cannot shed that energy, it doesn't arrive in the useful sense. It passes through, gathers what it can, and leaves. This is why studies of interstellar probes often look less impressive once capture is included. A quoted cruise speed describes the middle of the trip. It says little about whether the craft can turn that speed into an orbit, a landing, or years of work near the star. Shorter voyages help one cluster of problems. They reduce aging, delay, and cultural separation. At the same time, they worsen another cluster: braking, shielding, heat, mass, and precision. Slower flight eases some arrival demands while asking the mission to survive a much longer absence. The evidence doesn't select one best speed. It shows an exchange. Every profile solves one problem by enlarging another, and every kilometer gained during cruise returns at the destination as something the arrival system must absorb. That exchange gives us one rule worth carrying forward. Speed is not the solution. It is a choice about which problems the mission accepts and when it accepts them. A faster ship can shorten the years between departure and arrival. That protects living crews from aging and long separation. It also gives Earth and the travelers less time to grow socially distant. But the ship still has to arrive as a ship. Probe studies make this painfully clear. Their bold travel times often shrink once the plan includes capture. Flying past a star at enormous speed is one mission. Slowing down near it, staying there, and doing careful work is another. The second can demand far more equipment, energy, and mass than the headline suggests. A fast crossing means little if the probe flashes past its destination with no way to remain. Higher speed also makes small things dangerous. A grain of dust hits harder. Thin gas becomes a steady stream of impacts. Shielding grows heavier, and extra shielding must itself be accelerated. Then it must be slowed. Every fix joins the same bill. Technology can improve the bargain, sometimes by a great deal, but it cannot make momentum disappear. So the disciplined move after a successful crossing may be the least cinematic one. The ship does not plunge toward the new system because the target looks inviting. It approaches under control. It leaves room to brake, observe, revise the route, and preserve the machinery that carried it across interstellar space. Cruise speed wins applause. Arrival control keeps the mission alive. The trade-off remains. Getting there faster may reduce loneliness, delay, and the chance that generations lose contact with the purpose of the voyage. Yet the same speed raises the cost of shielding the ship and stopping it safely. There is no single setting where every burden fades. There are only different ways to distribute risk. A capable civilization might build engines powerful enough to cross the distance. Its harder achievement would be restraint, refusing to turn technical success into a reckless arrival. If the ship can reach another star but cannot protect its people, preserve its instruments, or stop where the work begins, what should a responsible ship refuse to do? Once the ship has settled above a promising world, we may see it as a delivery truck with nowhere else to go. The passengers have arrived, the engines can rest, and the planet below seems ready to take over. But ending the voyage doesn't make the ship disposable. Most cities aren't thrown away because the road trip ended. By then, the ship is much more than transport. It holds working life support, spare rooms, stored medicine, repair shops, records, tools, and places of refuge. Every part has already survived years of use, maintenance, and unexpected trouble. It is the only proven full-stack habitat the settlers possess. That word, proven, carries a great deal of weight. The planet may look gentle through telescopes and orbital surveys. Then the first landing teams may find radiation that reaches the ground. The soil may contain chemicals that damage crops or equipment. Debris may make certain orbits unsafe. Weather may ground aircraft for weeks. A landing site that looked flat from above may be impossible to supply through winter. None of this means the planet is unusable. It means the settlers may need time, and time is exactly what the ship can give them. Its life support system can keep people breathing while local habitats are tested. Its medicine can cover injuries and unfamiliar illnesses. Its workshops can rebuild broken machines instead of waiting for factories that don't exist yet. Spare volume can hold food, people, or damaged equipment. The records aboard preserve technical knowledge, crop data, maps, medical history, and instructions for rebuilding complex systems. If a surface settlement fails, the ship can take people back. If one region becomes dangerous, it can support a move elsewhere. If the planet proves far worse than expected, the ship may let the civilization remain in orbit, use moons or asteroids, or leave for another destination. Those choices disappear if the ship is stripped, abandoned, or sent into danger too early. Losing it wouldn't merely destroy an old vehicle. It would remove the civilization's hospital, warehouse, archive, factory, shelter, and tested environment in one blow. It would also erase the backup systems and skilled working spaces needed during any recovery. A whole city would be gone before the new city had learned how to keep anyone alive. So the first settlements should grow beside the ship, not at its expense. Materials can move downwards slowly. Systems can be copied before the originals are dismantled. Surface habitats can fail safely because refuge still hangs above them. The ship earned its value by surviving the voyage. Arrival doesn't erase that record. Until the new world can survive its own failures, the city in orbit remains the civilization's safest home. A planet can look welcoming from orbit and still be very good at killing visitors. The clouds may seem mild, the ground may appear firm, instruments may find water, useful minerals, and temperatures a person could tolerate. That earns a closer look. It does not earn the whole population. The trouble may be hiding in ordinary things. Dust could react with wet tissue, or work its way into seals. Soil chemistry could poison crops after weeks of healthy growth. A calm season could give way to winds that bury machinery or tear at exposed structures. Small debris above the surface might strike a landing craft at exactly the wrong speed. Even a safe landing site can fail if fuel production, spare parts, medicine, or power storage falls behind. None of these problems has to destroy a settlement by itself. People can test, adapt, and rebuild, but that only works while they still have somewhere proven to return to. A rescue plan is not much help if the rescue base came down on the same landing craft. The ship carries more than passengers. It holds the civilization's remaining reserve of people, tools, knowledge, food, and working systems. Every large descent transfers part of that reserve into an environment that has never supported a human life. If nearly everyone descends at once, one overlooked chemical reaction or one terrible season stops being a local accident. It becomes a loss the species may never recover from. It is like crossing thin ice with every person you know standing on the same sled. The far bank may be close, the ice may even look solid. Sending the whole group at once does not prove courage. It makes one mistake large enough to include everyone. This is where the spectacular move becomes the childish one. A mass landing feels decisive. It gives a rival a clean moment, with engines firing and a new world below. Yet all that drama comes from placing the highest possible stake on the least tested part of the plan. Caution changes the size of the gamble. Instruments go first, then machines, then small crews with supplies, rescue options, and enough time to discover slow failures. Crops need to pass several seasons, not merely sprout once. Shelters need to endure the worst weather anyone has measured. Local industry must show that it can make fuel, replace filters, repair tools, and keep people alive when shipments from orbit are delayed. That may take years. It may feel painfully slow after a voyage that consumed generations. But patience at this point is not fear. It is the final use of the ship's greatest advantage, a tested place to live while the new one proves itself. A civilization with one fallback should behave as though that fallback cannot be replaced. The planet does not need to be rejected. It needs to earn trust in pieces before one bad descent turns arrival into extinction. The first craft to approach the planet should be small. It should carry instruments, spare fuel, and only the people needed to bring it home. Behind it, the great ship remains in orbit, stocked, powered, and very much alive. That may look timid from the surface. After generations in transit, nobody will enjoy being told to wait above the world they crossed the dark to reach. The bravest-looking move would be a mass descent. Flags, crowds, open hatches. The wisest move is usually less satisfying. A beautiful planet can hide several ways to kill you. Its magnetic field may fail to block dangerous radiation. Its soil may contain chemicals that damage crops or lungs. Debris may crowd the safest orbits. Weather that seemed mild during one season may become violent during another. Even a friendly world can be hard to supply. A valley with water and good ground is little help if every landing nearby risks a crash. None of these failures needs to destroy the whole mission. They become fatal only if the civilization places everything within their reach. So the ship stops being merely a vehicle. It becomes the one proven city in the system. Its air system works, its farms have history, its workshops already turn stored material into repairs. People understand its alarms, its weak points, and its strange little habits. After centuries together, someone probably knows which pump needs a kick on cold mornings. That knowledge may be as valuable as any machine aboard. Leaving that city intact changes every smaller decision. Survey craft can test the atmosphere, then return. Robots can sample soil without carrying families. A surface team can build one shelter, live through a full year, and retreat if the design fails. A fuel plant can break down without trapping everyone below. Bad results remain painful, but they don't become final. A preserved ship makes every smaller move reversible. That is the operating rule. Redundancy sounds dull until you need it. You keep one working system while testing another. You don't replace the ship's farms until ground farms have survived disease, drought, and bad harvests. You don't empty its hospitals until surface medicine can handle an accident without help from orbit. Each success earns a larger commitment. Each failure costs equipment, time, and perhaps lives, but not the civilization itself. This restraint is active. It means launching probes, mapping hazards, building depots, and testing escape routes. It creates choices. The ship can support several landing sites, abandon a poor one, or wait for better technology. It can rescue a stranded team without evacuating an entire world. Once the whole population descends, those choices shrink very quickly. Before the city commits itself to the ground, what must it measure? Reconnaissance can sound like sightseeing before the serious work begins. A survey craft circles the planet, sends back a few impressive images, and someone chooses a landing site. But an image only tells you what the surface looks like. A settlement needs to know what that surface will do to people, machines, crops, and escape plans. The first question is radiation. How much reaches the ground, and how often does it spike? A beautiful plain may offer no protection. A less inviting valley, lava tube, or deep crater could cut the shielding a settlement must build. Then comes chemistry. Is the soil merely barren, or does it contain compounds that poison crops and damage seals? Can local rock supply metals, glass, concrete, or fuel ingredients? A mineral-rich site may save years of hauling mass down from orbit. It may also produce dust that works into every joint and lung. Weather changes the design again. Average conditions aren't enough. Planners need the worst winds, the longest cold periods, the flood paths, and the seasons when aircraft can't fly. They need to know whether a landing field stays usable after a storm. They need to know whether solar panels will spend weeks under dust, ice, or cloud. Resources matter only when people can reach them. Water buried 50 miles away is not the same as water beneath the habitat. A mountain full of useful ore may be worthless if vehicles can't cross the ground between. So survey craft map routes as carefully as deposits. They trace safe approaches, relay points, emergency shelters, and the shortest path back to a launch vehicle. And retreat belongs on the map from the start. If a reactor fails, where can the crew go? If the weather closes one route, is there another? Can a surface team return to orbit with damaged equipment? Can the whole outpost be abandoned without losing the machinery needed to try elsewhere? Explorers call this discovery. For settlement planners, it is how people avoid preventable deaths. That difference changes what the first settlement might be. The right site may not be on the surface at all. It could be an orbital station that studies several worlds while crews test short visits below. It could be a sheltered moon with poor scenery but easy access to ice. It could be a temporary mining camp designed to move when better measurements arrive. Reconnaissance is already settlement architecture. Each layer on the risk map changes which farms, shelters, power systems, vehicles, and rescue plans are possible. Good information works like a road, a pressure wall, or a spare engine. It supports choices before anyone has poured concrete. So the first plan should not name one world and close the case. It should map several places, several routes, and several ways home. Every measured fact must serve survival, because better maps decide what kind of civilization can safely be attempted. The first destination on our settlement chart may look less like a new home and more like a loading dock. It may be cramped, temporary, and completely unworthy of a flag. That's fine. No one brags about settling the safest loading dock first. But the loading dock may keep everyone alive, while the beautiful world below turns out to have poisonous dust, unstable ground, or no practical source of water. Choosing the first site is a ranking problem. Each location answers a different need and offers a different path for growth. Orbit offers distance. From there, the ship can study weather, radiation, landing zones, and possible resources without sending everyone down. Supplies remain close. Engines remain available. Communication and rescue are simpler when the crew stays near its largest machine. If the planet delivers an ugly surprise, leaving is still possible. A small moon or asteroid offers material. It may hold water ice, metals, or carbon compounds that robots can collect before a large settlement exists. Those resources could become drinking water, shielding, building material, or propellant. You wouldn't want to live there. It can still help the settlement grow. A sheltered surface site answers another problem. A lava tube, crater wall, or thick layer of soil may reduce radiation and soften temperature swings. It might sit far from the most striking landscape, yet a plain hollow with water nearby could be worth more than a grand valley that leaves every habitat exposed. Then there is retreat. Retreat isn't a site in the usual sense, but it belongs on the same chart. A crew needs somewhere to go if a reactor fails, A storm lasts too long, or local dust ruins machinery faster than expected. That refuge might be the main ship, an orbital station, or an earlier camp that remains stocked and working. These aren't rival answers, they form a sequence. Orbit can support robots sent to nearby rocks. Those rocks can supply a sheltered camp. The camp can test farming, repairs, and surface travel before we build anything too large to abandon. That changes the ranking. Reversibility may outrank scenery. A place that allows a cautious arrival, a practical test, and an orderly departure can beat a place with greater promise but no forgiving first step. The order can change as measurements improve. A temporary camp may become permanent. An orbital station may shrink once the surface proves safe. Retreat routes may become trade routes. The aim isn't to avoid commitment forever. It's to make each commitment after the system has earned it. So the settlement begins as branches on a chart. Ship to orbit, orbit to rock, rock to shelter, with every branch still connected to a way back. Once the survey reports begin arriving, choosing a home can feel like an act of courage. Someone studies the star system map, points to the most inviting world, and says, "There." But that single mark may be the least important part of the plan. A settlement plan pinned over a map should look less like a destination and more like a set of usable choices. One branch may lead to a stable orbit, where the ship can remain supplied while crews study the system. Another may lead to a mineral-rich asteroid that can provide metal and water without a landing. A third may lead to a sheltered site on a moon, protected from radiation or violent weather. None of those places has to become the final home. That's the change. The first site doesn't need to be scenic, Earth-like, or even on a planet. It needs to preserve valuable options while removing the worst ones. An orbital base can wait. A mining camp can move. A surface city is much harder to reconsider once its foundations, power lines, and people are in place. Bad first maps create bad first commitments. A missing radiation belt can turn a promising orbit into a trap. A shallow reading of the minerals can send heavy equipment toward rock that cannot support it. A short weather survey can make a mild season look permanent. By the time people discover the error, the fuel, machines, and lives may already be in the wrong place. So map quality becomes civilizational quality. A clear map gives the first settlers room to compare, delay, divide resources, and change course. A weak map forces them to improvise around surprises that should have been found earlier. That difference will reach into everything they build, their transport routes, their power system, their food reserves, even the way authority works when two sites need the same equipment. The first architecture of civilization is an information architecture. Before there are streets, pressure walls, farms, or workshops, there are measurements arranged into decisions which orbits stay stable, which rocks contain water, which valleys receive enough light, which sites can communicate with the ship, which routes remain open after an engine fails. Humans are rarely patient with this stage. We like the decisive arrival, the flag, the first footprint. A chart full of conditional routes feels less satisfying. It resembles planning a warehouse more than founding a world. Yet the future settlement can only be as flexible as the choices its map preserves. And once that becomes clear, a very human shortcut appears. Why make people spend years collecting all of this when we can invent one heroic machine to do it first? Why not send robots ahead? Sending machines first is exactly the clever idea any frightened civilization reaches for. And it's a good idea. Robots don't need air, sleep, food, or a hurried rescue when a cable snaps. They can survey the ground before anyone trusts it with a habitat. They can haul shielding, grade roads, bury pipes, and assemble landing pads. They can handle dangerous maintenance beside reactors and fuel plants. They can repeat the same construction task 10,000 times without getting bored or missing home. If one machine fails, no family receives the call. Distance may even suit them better than it suits us. A delayed command is annoying, but it doesn't make a robot lonely. Give the machine a clear job and enough local control, and it can keep working while its operators wait for the next message. A raw site can slowly fill with roads, cables, storage tanks and shelters before the first crew arrives. That promise is real. The limit comes from what keeps those machines alive. A loader needs power. The power system needs spare parts. Spare parts need materials, tools, and accurate fabrication. Fabrication equipment needs maintenance. Maintenance needs diagnosis and control. Each layer rests on another layer, often one that still exists back on Earth. You can think of this as a closure ladder. The first rung is power. Can the site produce and store enough energy? Then come materials. Can it mine, refine, and shape local rock or ice? Then fabrication. Can it turn those materials into useful parts? After that comes repair. Can machines detect wear and restore one another? Finally, control. Can the whole system respond when events fall outside its original instructions? A settlement climbs that ladder gradually. Early robots may unpack solar panels but not manufacture them. They may print simple brackets but still depend on imported bearings, sensors, lubricants, computer chips and seals. They may replace a broken motor if the replacement arrived on the cargo ship. Making that motor from local material is a much taller rung. This is why robotic bootstrapping depends on ordered steps. The mine cannot supply a refinery that has no power. The repair shop cannot fix machines before it has tools. The tools cannot be made locally until the site can produce materials of reliable quality. One missing dependency can leave a very capable machine waiting beside a useless pile of equipment. So the measure of a robot isn't how impressive it looks while working. It's how much of its support chain the whole robotic system can sustain. Send robots first, certainly. Send them in waves, with spare capacity and repair loops behind them. The danger falls as closure rises, one working rung at a time. A workshop can stop because of a part small enough to rest on a fingertip. One cracked seal, one worn cutting edge, or one damaged sensor can turn a powerful robot into very expensive furniture. That sounds like a hardware problem. It's also a timing problem. A robot may know exactly what failed, yet still lack the material, tool, or working machine needed to replace it. If the replacement must come from Earth, the repair loop stays open until another shipment arrives. Across interstellar distance, that delay could last years. Meanwhile, every machine that depends on the broken one has to wait. So intelligence alone doesn't create autonomy. Software can diagnose a broken pump. It cannot make a fresh seal without the right material and a machine that can shape it. The settlement also needs a way to check that the new part will hold pressure. Each ability depends on earlier abilities staying alive. Electronics make this harder. A workshop might cast metal brackets, sharpen worn tools, and rebuild simple motors. Damaged sensors and computer parts sit much higher on the ladder. They need pure materials, controlled manufacturing, and equipment that may itself depend on imported electronics. The robot repairing the factory may be waiting for a chip used by the machine that makes chips. Industrial independence has a sense of humor. This is why partial closure is the better measure. Ask how far a repair can travel before it reaches an imported part. A shallow system can tighten bolts and swap sealed modules. A deeper one can open those modules, replace their common failures, make the needed tools, and restore the machines that support the workshop. Deeper still, it can produce some of its own sensors, wiring, lubricants, seals, and control parts. No single mission closes every loop. Current research can test pieces of the chain, from robotic mining to automated inspection. It cannot show that a machine community will sustain itself between stars. Too many failures interact, and the rare ones may be the worst. A seal ages, dust enters a bearing, a sensor drifts, then the repair tool fails halfway through the job. That doesn't make sending robots first a bad plan. It makes it a program built in layers. Early machines scout and prepare. Later waves bring broader tools, duplicate systems, and parts chosen from real failure data. Humans enter the timing only when the repair chain is deep enough that their survival won't depend on every shipment arriving intact. Every miracle machine eventually becomes a spare parts problem. The useful settlement is the one that can solve more of those problems locally, then use each repair to protect the next. Robots can go where we would rather not send a person yet. They can work beside unstable ground, handle toxic dust, and sit through months of delay without needing food, sleep, or reassurance. If one fails, the loss is painful and expensive. It is not a funeral. That gives us something more valuable than speed. It gives us time. Machines can test a site before people depend on it. They can bury power cables, prepare landing areas, store supplies, and build shielding. They can also expose bad plans, while those plans are still made of metal and money, rather than occupied rooms. But sending robots first does not mean pressing a button and waiting for a finished city. Each task depends on something else being ready. A digging machine needs power. The power system needs clean surfaces and working connections. Both need inspection, spare parts, and tools able to reach the broken piece. Even the repair robot may need another robot to pull it out of a hole. Mars, with some patience, can turn a simple maintenance schedule into a family tree. So the order matters. First come machines that measure and prepare. Then come systems that protect power, move material, and maintain basic equipment. Later arrivals can add workshops, better diagnostics, and the ability to make simple replacement parts. Each layer supports the next. The settlement becomes less dependent on Earth by degrees, not through one sudden leap into autonomy. Imported complexity remains the stubborn part. A robot may shape a beam from local metal long before it can make a reliable computer chip, a precision bearing, or a medical sensor. Local production can close the easy loops first: water, oxygen, shielding, rough construction, and some fuels. Harder loops stay open to Earth for much longer. That is not failure. A civilization is not cheating because it refuses to move all the way in on day one. This is why the shallow ladder leads directly to where people live. If robots can prepare only a landing pad and a power line, the first crew needs a heavily supplied habitat. If the machines can also bury rooms, stock water, check seals, and keep the power system alive, people can arrive with a wider safety margin. The depth of local repair and production determines what kind of home is possible. Robots absorb danger, and they delay the moment when human lives must be committed. They do not remove that moment. Eventually, someone has to sleep under the shielding, eat from the stores, trust the air system, and wake up knowing Earth cannot send help quickly. So when the machines have done enough, what does the first human settlement actually feel like to live in? The planet is right there beneath the windows, close enough to fill half the view. After traveling so far, staying in orbit could feel like stopping at the front door. But a door isn't always the safest place to sleep. The surface may have dust, violent weather, deep cold, or radiation that shelter cannot yet block. A small mistake can trap a crew far from its ship. Even reaching orbit again may require fuel, working engines, and a launch site that survived those harsh conditions. An orbital home changes that calculation. The crew can live inside a vessel built and tested near Earth. Its air, water, power, and shielding can be checked before the long trip begins. Food and spare parts stay close. If something fails after arrival, the return ship is already attached or nearby. No one has to climb out of a gravity well before heading home. That easier return is more than comfort. It gives the crew choices. They can wait out bad weather, move to another orbit, or leave if the surface equipment stops working. On the ground, those same problems may close every exit at once. In orbit, a bad week doesn't have to become a permanent emergency. This doesn't mean the crew ignores the world below. They can study it closely, guide equipment with almost no communication delay, and visit chosen sites for limited periods. Samples and supplies can come back to the orbital shelter. Each trip shows what the surface demands before anyone tries to live there for months. The first foothold may even sit beside a small moon or asteroid near the target world. A base there could offer raw material, weaker gravity, and a simpler route back into space. It might look less impressive than a flag beside a habitat. It could also keep more people alive. Human history doesn't usually build the loading dock last. We establish the safe place where food, tools, spare parts and transport can gather. Then we push farther from it. Space settlement may follow the same ordinary logic, even when the planet below is the reason everyone came. There will still be a powerful pull toward planetfall. Boots in dust make a clean symbol. Windows looking down from a safer home don't carry quite the same romance. Yet the rational choice and the romantic choice can point in different directions. Orbit first is not failure. It is a human presence at another world, with people living, working, learning, and returning safely. The surface can wait until shelter and transport are ready. Progress doesn't become less real because the first home has no ground beneath it. The first settlers may have several homes before any one of them feels permanent. A cabin in the ship could remain safer than the world they crossed space to reach. The ship already has air, power, medical equipment, and known escape procedures. Its crew understands every pump and alarm. You can see the appeal. But a ship designed for travel may be cramped, hard to repair, and expensive to keep running. It may also provide little gravity during a long stay. A vehicle can become a home, but that doesn't make it a comfortable one. An orbital habitat offers more room and can be built for years of use. It stays close to the target world without taking on every surface hazard. Supplies can arrive there first. Crews can study weather, dust, radiation, and landing sites from above. If the surface team gets into trouble, they have somewhere nearby to return. Then there may be another option, a moon, asteroid, or other small body that is easier to reach. Low gravity can make landing and launching less costly. Local ice might provide water, oxygen, or fuel if surveys confirm it can be extracted. The trade-off is that low gravity may harm human health, and a small world may offer almost no natural shelter. Easy transport doesn't automatically mean easy living. So the first settlement works less like one isolated town and more like a group of connected places. The ship carries people and equipment. The orbital habitat protects the main population. A nearby body may store fuel or raw material. Small teams descend to the target surface while return vehicles wait for them. Each inhabited place supports the others. That arrangement can look awkward. People may travel all that way, then spend years living above their intended home. Children might call a rotating station home, while adults still refer to it as temporary. Civilizations have begun in stranger accommodations. The advantage is reversibility. If one landing site floods, freezes, or fills with abrasive dust, the whole settlement doesn't fail with it. If a habitat develops a serious fault, people can move elsewhere. Supply routes can change. New evidence can change the order of construction without turning every earlier decision into a disaster. Shelter, supply, gravity, and escape all pull in different directions. No single location wins every comparison. The right sequence will depend on the world, the vehicles, and what early crews discover after arrival. A port may come before a city. At first, that port could be a ship, a station, and a small outpost linked by careful flights. Lights would move between them against the dark, carrying food, tools, and people home. That first port would be less like a young capital and more like a working harbour. It would have docks, fuel tanks, spare parts, sealed storerooms, and several places to sleep. Some might orbit the planet, others might sit on a nearby moon or on the surface below. Together, they would form one living network. The phrase matters because it changes what counts as arrival. We tend to expect the first settlers to plant themselves on the main world and stay there. Anything less can feel temporary, almost as if the mission hasn't properly started. But permanence is a poor test during the years when every landing still teaches you something new. A port can do much of the work people expect from a city. It can receive cargo, repair vehicles, store emergency supplies, and give tired crews somewhere protected to recover. It can send people down for weeks or months, then bring them back before their equipment wears out. The surface outpost may grow slowly, while the larger station carries the heavier burden of keeping everyone alive. You can think of it as moving into a difficult house while keeping the moving van close. You haven't failed to move. You've simply kept food, tools, and a warm place within reach until you know which rooms leak. That makes the whole arrangement reversible. A habitat can be moved, rebuilt, or abandoned without ending the settlement. A depot can shift to a safer orbit. Supplies can be divided so one accident doesn't take everything with it. If the first surface site proves colder, dustier, or less stable than expected, the people don't have to defend a bad decision because it once looked brave. The mission can advance while its first homes remain provisional. Crews can map routes, test shelters, learn local seasons, and begin producing water or fuel. Each success makes the next step less dependent on Earth. None of this requires pretending that a warehouse is a boulevard. It only requires admitting that history often builds the warehouse first. And this port is not a center for trade between star systems. There may be no other human settlement within light years. Its traffic is local. Ship to station, station to surface, surface back to safety. Food goes one way. Samples and broken equipment come the other. People move wherever the risk is lowest that week. Over time, one outpost may become the city everyone expected. Roads may replace flight paths. Workshops may become factories. Temporary rooms may fill with families who no longer think of them as temporary. But during the uncertain beginning, the settlement's most important address may still be the vessel that carried it there. So why might the ship remain central long after the first people step outside? Once a settlement has working rooms, stocked workshops, and regular trips to the surface, the founding ship can look strangely excessive. It is enormous, expensive to maintain, and full of material that could become walls, pipes, or machinery. Taking it apart may seem practical. But its metal is probably the least valuable thing aboard. The ship is still a habitat, with air and water systems built for years of continuous use. It is an archive holding technical records, scientific knowledge, laws, maps, and the settlement's own history. Its medical rooms form the best hospital available. Its classrooms make it a school. If fire, contamination, weather, or equipment failure closes part of the settlement, the ship becomes an emergency shelter large enough to keep people alive. More important, every major system aboard has already faced its hardest test. The life support worked through the voyage. The power system survived years without a repair depot nearby. Medical equipment treated real patients far from outside help. Procedures were revised after real failures by people who had to live with the results. That history doesn't weigh much, but replacing it could take decades. A new water plant on the surface may be more efficient. It has also never endured a bad season, a cracked seal, or an operator making the wrong choice while exhausted. A new clinic may have brighter rooms. It may not yet have enough staff, spare parts, or experience with local hazards. Proven systems are boring right up until something else fails. We tend to notice redundancy only when the main system stops working. By then, choices narrow fast. Keeping the ship intact gives the settlement a second place to breathe, heal, teach, and recover. It also preserves the people who know how those systems behave. The engineer who remembers an unexplained pressure drop is part of the air system. The medic who knows which supplies became scarce during the voyage is part of the hospital. Air, water, medicine, and institutional memory remain tied together. For a while then, the ship is more than transport. It is a backup copy of civilization, already tested under conditions harsher than the young settlement has faced. Lit from within while the new towns grow around it, it stands like a reserve city, occupied, maintained, and ready. Only when replacement habitats, hospitals, archives, schools, and life support networks have survived years of ordinary use does dismantling the ship become a reasonable bargain. Until then, its salvage mass is worth far less than the civilization it can still save. Once the first settlement is standing, the ship begins to look less like a refuge and more like a warehouse. There are beams in its hull, pumps behind its walls, cables under every deck, and spare machines packed into compartments. Workers can see months of construction waiting inside one object. The temptation is perfectly practical. Remove a pressure door and a new workshop gets one today. Pull out a water pump and the farming system gains a tested spare. Cut apart an unused deck and several homes get strong metal without waiting for a mine, a refinery and a factory to catch up. Efficiency can be a lovely word for cannibalizing your only lifeboat. The problem isn't the first part removed. It's the shrinking number of ways to recover when something else fails. A ship may have several air pumps because one pump can seize. It may carry separate power lines because a fire can cut the main line. Its medical bay may duplicate tools already placed in the settlement. But those duplicates become precious after contamination, a building failure, or a run of injuries. Each useful piece taken from the ship can create something valuable outside it. At the same time, each removal makes the ship less able to serve as a complete refuge. Eventually, the engines may still work, while the air system cannot support everyone. The medical rooms may remain clean, but lack power. The archives may survive, while damaged cooling equipment threatens the computers holding them. That is how a backup turns into a collection of parts. Nothing looks disastrous on the day it is removed. The danger appears later, when several failures arrive together and the settlement discovers that its reserve can no longer do the whole job. Engineers call this a single point of failure. One broken part, one damaged building, or one contaminated water loop can stop an entire system because no independent replacement remains. A young settlement is crowded with these weak points. It has few hospitals, few workshops, few trained crews, and perhaps only one reliable source for a critical material. Keeping the ship whole gives those systems somewhere else to fail safely. This doesn't mean the ship must remain untouched forever. It means dismantling should follow proof. Replacement systems need years of ordinary use. Crews need to show they can repair them without borrowing the ship's tools. Hospitals, archives, power, water, and air must each have backups that don't depend on the same building or supply line. Only then does salvage become simple arithmetic. Before then, a steel beam in a new roof may cost far more than its mass suggests. It may be the beam that leaves the last complete refuge unable to close its doors. The threshold isn't the first successful harvest, or the first month without an alarm. It comes when losing part of the ship would no longer put the settlement in danger. Until then, the ship carries more value than anyone can measure by weighing its metal. A pressure hull can become rooms, tunnels, storage tanks, or workshops. Life support equipment can keep a growing settlement supplied with clean air and water. Medical systems may be the only ones capable of handling surgery, infection, or a difficult birth. The ship's archives could hold repair manuals, scientific records, software, maps, and pieces of human history that exist nowhere else nearby. Cut those systems apart too early, and reuse starts to look a lot like panic. The parts may solve today's shortage while removing the only answer to tomorrow's failure. A water recycler moved into the settlement is helpful. A water recycler removed before its replacement survives 2 bad seasons is a gamble. Timing changes everything. Once local systems have worked long enough to earn trust, salvage stops being an act of desperation. It becomes a choice. Engineers can compare what a module provides aboard the ship with what it could provide somewhere else. They can remove it because another system has already proved itself, not because a shortage has left them cornered. That doesn't require keeping every bolt in place until the entire settlement is secure. Partial salvage can begin earlier. Empty cargo frames might become bridges. Spare shielding might protect a clinic. An unused landing structure might supply beams for a second power station. The rule is simply that each removal must leave a survivable failure behind it. If this part disappears, can something else do its job? That distinction may look cautious, perhaps even wasteful. Settlers will be surrounded by finished machinery while building rough local copies from limited materials. Someone will certainly point at a sealed compartment and say, with understandable irritation, that it would make an excellent kitchen. They may be right, but if opening it weakens the last emergency shelter, dinner can wait. A young settlement still needs the ship because too many failures can meet in one place. Later, those failures become separated. Power comes from several sites. Medicine is stored in more than one clinic. Knowledge survives in more than one archive. Losing one system becomes painful without becoming fatal. And that may be the next test. An outpost survives by protecting everything it cannot replace. A colony begins to absorb losses and continue. So what positive threshold tells us that a settlement has crossed that line and become a real colony? The first convincing sign may be a greenhouse. Green rows sit under glass, tomatoes hang from vines, and the air smells faintly of wet soil. After months of packaged meals, that first fresh harvest would feel like a declaration. People are eating food grown here, plants are helping refresh the air. Surely this is a colony now. It isn't. Not yet. Food production is essential, and growing it far from Earth would be a major achievement. No settlement can become independent while every meal arrives by ship, but biological survival is necessary and shallow compared with the systems supporting it. A greenhouse can look alive while remaining completely dependent on Earth. Consider one water pump beneath those tomatoes. It moves a measured flow through pipes, filters, and roots. If its bearings wear down, the plants don't care how successful last month's harvest was. The crop begins losing water. Heat builds in the greenhouse. A small mechanical failure starts a clock. Tomatoes do not manufacture bearings, nor do they make replacement seals, cut precise threads, sterilize surgical tools, or rebuild a damaged valve. They don't produce clean tubing after mold reaches a waterline. They can't test a pressure vessel for a crack too small to see. All of that comes from another layer of survival. It is less photogenic than green leaves, but far harder to replace. A working farm rests on pumps, sensors, lamps, cables, filters, nutrients, software, and people who understand them. Those parts rest on tools. The tools rest on materials, calibration, power, and still more tools. Even sterilization has its own chain. You need heat or chemicals, sealed equipment, reliable measurements, and clean handling. Miss one link, and a healthy crop may sit beside a failing habitat. This doesn't make the greenhouse symbolic or unimportant. It makes its success more demanding. Growing food proves that people can manage a living system away from Earth. Independence asks whether they can repair the machinery that keeps that living system alive. A true colony, therefore, needs more than stored spare parts. Spares only postpone dependence. It needs the ability to diagnose failures, shape materials, make common components, verify that they work, and return damaged systems to service. It also needs technicians who can teach those skills before knowledge leaves with one person. Some rare parts may still come from Earth. Complete isolation isn't the standard. The stricter test is whether ordinary breakdowns can be handled locally without placing everyone on a rescue timetable. That boundary is easy to miss because crops are visible. Maintenance capacity hides in workshops, cleaning rooms, inventories, and the practiced hands of technicians. Yet those plain rooms may tell us more than the greenhouse does. An outpost can grow dinner. A colony can keep the pump running long enough to grow the next one. A settlement can look surprisingly complete while depending on one small crate from Earth. The greenhouse is bright. The storage tanks are full. Meals come from local crops. Then a pressure regulator fails, and the replacement was supposed to arrive 8 months later. That regulator belongs to a much deeper stack. Start with the walls holding the air in. They need seals, sensors, pressure hardware, and patches that remain safe through years of heating and cooling. Pumps move water, waste, fuel, and air. Valves decide where those fluids go. Filters catch dust and chemicals before they reach your lungs. Each part seems ordinary until there isn't another one. Then come the tools needed to reach those parts. Wrenches and cutters are only the beginning. A workshop needs measuring devices, welding gear, clean surfaces, lubricants, fasteners, spare wire, and material that can be shaped into something new. The people there also need transport. A broken rover can leave a technician farther from shelter than anyone can walk. Fixing the air system may first require fixing the vehicle that carries the tools. Medicine adds another layer. Growing food doesn't produce antibiotics, sterile tubing, replacement teeth, surgical blades, or the chemicals used in tests. Even basic care depends on refrigeration, clean water, protective clothing, and machines that can be calibrated. A clinic without supplies slowly becomes a room where trained people know exactly what they cannot do. Electronics make the stack stranger. A cracked handle can be machined. A failed control board may need pure materials, tiny printed paths, special chemicals, and equipment that checks features too small to see. Computers run the pumps, track supplies, guide vehicles, and preserve technical records. So the knowledge system needs protection as well. Manuals must survive. Software must remain readable. Measurements, repair histories, and design files need copies that people can find when the network is down. This is why local farming is necessary, but it sits near the top of the dependent stack. Beneath it are layers of industrial precision. The settlement doesn't have to manufacture every advanced component. It does need enough substitutes, spare capacity, and repair skill to keep one missing item from becoming a deadline for evacuation. That gives us a practical definition of colony status. The settlement has reached it when local replaceability is strong enough to outlive the ship that brought it there. If the ship never returns, pressure hardware can still be maintained, pumps and valves can still be replaced. Tools, transport, medicine, electronics, and technical knowledge can keep passing from one working generation to the next. Civilizations are rarely defeated by a shortage of grand plans. Sometimes the decisive object is a seal, a bearing, or a bottle of reagent that nobody learned to make. A farm can feed the people waiting for that part. Independence begins when they can make a working answer before the last spare is gone. A thriving greenhouse can make a settlement look more independent than it is. Green leaves, full storage rooms, and a busy workshop suggest the difficult part is over. People are eating local food. The lights are on. Everyone looks occupied. But growing dinner is only one layer of survival. The greenhouse depends on clear panels, lamps, pumps, sensors, filters, nutrient chemicals, and thousands of joints that must stay sealed. A good harvest proves the farm works today. It doesn't prove that people can rebuild the farm 20 years from now. So give the settlement one severe test. Suppose the founding ship vanishes tomorrow. No warning, no final delivery, no chance to unload the stores still inside it. Does the community below still have a future? This isn't mainly a test of courage. The settlers may be confident, organized, and committed to staying. None of that can turn a worn bearing on a lathe. Confidence helps people work through a crisis. It cannot replace the industrial system that keeps producing parts after the crisis becomes ordinary life. That boundary separates a busy outpost from an operational colony. An outpost can run beautifully while its strongest support remains nearby. It may grow food, recycle water, train children, and expand its living space. Yet some vital machines still lead back to the ship. Their spare parts came from its holds. Their calibration tools sit in its workshops. Their control boards may have no local substitute. You can see the problem even in a well-equipped machine shop. A lathe can shape metal, but it needs cutting tools, lubricants, motors, bearings, and accurate measuring devices. Those devices need their own parts and standards. One workshop doesn't equal an industrial base. It may simply be the final link in a supply chain that begins somewhere else. And the dependents can hide for years. Warehouses may hold enough replacements to make every failure seem manageable. Then one uncommon sensor breaks, or the stock of a certain chemical runs out. The settlement discovers that stored abundance was only borrowed time. A colony passes the loss of ship test when those hidden threads can break without taking daily life with them. The vessel can disappear, and the settlement continues. Not comfortably in every case. There may be shortages and painful choices, but its systems can be repaired, copied, adapted, and eventually replaced. It's like removing scaffolding from a building. While the scaffolding stands, the building may look finished. We can walk through the rooms and switch on the lights. The test comes when the temporary support is removed. If the walls hold, the building is carrying itself. If they don't, completion was only an appearance. Here, The scaffolding may contain machine shops, medical stock, chemical feedstocks, computing hardware, and experts who cannot be replaced quickly. Losing it exposes every dependency at once. Success is what remains after the strongest crutch is gone. So which industrial branches must mature before the settlement can lose the ship and keep its future? Many stories would call the settlement independent as soon as its mines are working and its lights stay on. But power and raw rock are only the bottom rungs of a much longer industrial ladder. First, the settlement must produce steady energy. That energy runs drills, pumps, furnaces, and chemical plants. Extraction then brings up water, metals, carbon-bearing material, and other feedstock. Refining separates those materials into forms a workshop can actually use. Only then can fabrication turn them into pipes, panels, bearings, wire, glass, seals, and machine parts. Each workshop depends on the ones below it. A metal shop needs refined alloys. The refinery needs pumps and heat. Those machines need replacement valves, sensors, lubricants, and control circuits. Maintenance holds the chain together, because a factory that cannot replace its worn parts is slowly consuming itself. Control comes later. The settlement must make enough motors, instruments, switching equipment, and computing hardware to run its growing industry without constant shipments. You can see the awkward part when a failed temperature sensor stops a furnace worth thousands of times more. The grand machine may be waiting for one tiny part in a padded box. So independence does not arrive as a checklist of finished factories. It grows through ordered closures. Power supports extraction. Extraction feeds refining. Refining supplies fabrication. Fabrication makes maintenance possible. Maintenance protects every earlier step. Better control then raises the output and precision of the whole chain. Some branches will close sooner than others. Basic structures, pipes, tanks, and rough machine parts may become local fairly early. Precision bearings, advanced electronics, sterile drugs, diagnostic chemicals, and specialized medical supplies are likely to remain difficult much longer. We could see a settlement build another habitat while still depending on Earth for a vial of medicine or a chip that controls its air system. Civilization, at this scale, is tools rebuilding tools. Factories keep the other tools alive, and those tools return the favor. Real industrial independence begins when that chain can repair itself, expand itself, and survive the loss of its most difficult imports. A mine and a reactor make an impressive start, but they don't make a society. The mine supplies metal, the reactor supplies electricity. Neither can keep a surgeon's hands clean or stop a seal from cracking inside an oxygen pump. That seal may need a specific polymer. Making it takes chemical feedstocks, controlled heat, clean vessels, and people who know the process. The vessels need pumps, and the pumps need lubricants. Those lubricants require another chemical process. Someone must test every batch. Grease that works in a loading crane might release poisonous gas inside a habitat. Storage adds another branch. Food, fuel, gases, medicine, and reactive chemicals need different containers. Some must stay cold, some must remain sterile, others must never meet water or oxygen. Without safe storage, local production creates materials the settlement cannot keep. Then everything has to move. Roads, cargo vehicles, pressure locks, loading gear, batteries, tires, rails, and navigation systems join the chain. A broken transporter can stop a clinic from receiving oxygen, even while the oxygen plant works perfectly. Clinics widen the diagram again. They need trained doctors, sterile rooms, diagnostic tools, antibiotics, anesthetics, dental materials, and reliable refrigeration. You could produce tons of steel and still lose someone to an infected tooth. People remember the mine. We tend to forget the gasket, the antibiotic, and the textbook. That textbook belongs to another branch. Skills must be saved and passed on. Engineers age, surgeons retire, children arrive knowing none of it. Schools, workshops, laboratories, technical records, and apprenticeships are part of the machinery. Knowledge can fail as surely as a bearing. The colony diagram keeps blooming. Mines feed chemistry. Chemistry feeds medicine and manufacturing. Transport connects every branch. Storage protects their output. Training brings in the next generation. Each branch depends on several others, and the slowest one sets the pace. Some of the last imports may fit in your pocket. A precision sensor, a sterile drug, a specialized chip. Around that tiny missing piece stands an entire local society, with mines, clinics, schools, factories and trucks all waiting. A settlement can look successful long before it can replace everything it uses. The streets may be busy, the farms may be feeding thousands, steel may leave the foundry each week. Then a sensor fails inside a water purifier, and nobody nearby can make another one. That mismatch is easy to miss. Bulk industry gives us the most visible signs of progress. Mines produce ore by the ton. Refineries turn it into metals, glass, fuels and fertilizers. Heavy machines move across the ground. Yet the last problem is often the tiny clean thing inside the heavy one. A precision sensor needs carefully purified materials, exact measuring tools, controlled rooms, stable power and trained people. Those tools contain their own precision parts. The machines that make those parts need calibration equipment. That equipment may depend on specialized electronics, coatings, gases or chemicals made somewhere else. So local industry grows as a chain of dependencies, with branches feeding other branches. You cannot finish them one at a time and cross them off a list. A clean process may need a sensor made by an electronics shop. The electronics shop may need a chemical from a refinery. The refinery may depend on pumps, whose seals require another chemical process. Every new ability creates several more requirements behind it. Medicine brings the same problem into the clinic. A familiar drug may require a rare precursor, sterile vessels, filters, testing equipment, cold storage, and careful quality control. Making something that looks like the drug isn't enough. The dose must be pure, stable, and safe. That standard is harder than producing another load of concrete. None of this means full local replacement is impossible. It means the pace will probably be set by precision components, clean processes, sensors, and medicines long after the settlement masters bulk materials. Imports may shrink from cargo holds of machinery to a few sealed boxes each year, but those boxes can still carry parts that keep hospitals open and factories accurate. The settlement may appear independent from a distance while remaining tied to Earth by one drug precursor or one instrument small enough to hold between two fingers. Its progress is real, so is the dependence hidden inside it. It's tempting to judge the settlement by averaging everything together. Its farms expand each year. Its mines produce more metal. Its workshops make a larger share of the tools people use. If you put all those gains on a chart, the line rises, but an average can hide the one branch that still leads back to the ship. Local industry grows as a chain of dependencies, not a checklist of finished jobs. A furnace needs controls. The controls need sensors. The sensors need purified materials and precise equipment. That equipment needs its own replacement parts. If one indispensable branch stays open, the whole chain may stop there. A town can make 10,000 ordinary bolts and still depend on one imported bearing. It can build hospital rooms while importing the medicine used inside them. It can grow food, refine fuel, and cast steel, yet remain unable to replace a failed instrument in the clinic. The largest industries don't always set the pace. The slowest indispensable one does. That gives colony status a harder test. The question isn't whether most goods are local or whether imports have become small. It's whether the settlement can replace every part whose loss would stop essential systems. One missing branch can stall the whole civilization. The branch might be tiny in mass and enormous in consequence. Precision components and medicine will likely remain among the last hard bottlenecks. Both demand more than raw material. They need controlled spaces, reliable measurements, clean processes, and workers who can catch errors before those errors spread. Each of those abilities rests on another layer of tools and knowledge. So the settlement moves at the speed of the part it still cannot replace. Closing that final branch may require less cargo than building the first mine, but far more accumulated skill. Machines still matter here, though they aren't the final limit. Every process must be learned, practiced, checked, and taught again before its experts are gone. That turns the industrial problem into a human one. A colony needs enough people to staff every essential branch without leaving a single expert as the only link. It also needs students, teachers, records, practice, and time. Can a settlement keep that ladder of knowledge intact across generations, with enough people to climb it? A census board can show a healthy population and still hide a fragile settlement. The total says how many people are alive. It doesn't tell you whether 3 reactor technicians are nearing retirement, or whether the only surgeon has anyone ready to take her place. One model found that 98 people could complete a very long space voyage without the population collapsing. It's an intriguing result, and also a good example of why a clean number can be dangerous. 98 wasn't a universal minimum. It came from a particular simulation, with particular rules for pairing, birth rates, accidents, and the ages of the people aboard. Change those rules, and the answer changes too. That's because a population isn't a jar of identical beans. People age, they become ill. Some cannot or choose not to have children. An accident might remove 2 people who share the same rare skill. A run of births at the wrong time can leave too few working adults supporting too many children and older people. The headcount may look steady while the settlement loses options. So viability becomes a management problem. The community needs education that survives its first teachers. It needs reproductive choices that protect both individual dignity and the future age balance. Essential jobs need overlap, so no repair, medical procedure, or production line depends on one person getting out of bed that morning. Even records aren't enough. A manual cannot watch a student make a mistake, correct it, and confirm that the skill has truly passed on. And there's a stronger test than keeping one habitat alive. Can the population establish a second habitat that no longer depends on the first for daily survival? Until then, one fire, infection, crop failure, or structural fault can still threaten everyone at once. 2 independent settlements create a form of human redundancy, much like duplicate pumps or separate power lines. No study can give one final passenger count for every ship and every future society. The number depends on biology, technology, institutions, luck, and how much failure the settlers can absorb. A durable population isn't the smallest group that avoids extinction in a model. It's a community large and capable enough to lose people, teach replacements, preserve choice, and eventually build another home. A settlement can have enough people and still be one accident away from losing a skill it cannot recover. If the only person who can rebuild a water pump becomes ill, the problem is no longer just medical. Surgeons, machinists, agronomists, electricians, teachers, and archivists are all part of life support. Some keep bodies alive, some keep crops growing, some keep power moving. Others preserve the knowledge that lets the next person do those jobs. The machines and the people belong to the same system. That makes overlap essential. One surgeon is a point of failure. 2 surgeons are better, but only if both can train others. The same applies to every skill the settlement cannot safely lose. A machinist must know how to shape a replacement part. Someone else must maintain the lathe. An electrician must keep the workshop powered. An archivist must protect the drawings, manuals, and records that connect all 3. Tools wear out slowly enough to fool you. Knowledge can vanish in a day. A civilization fails when it loses skills faster than it can replace tools. Every later breakdown becomes harder to repair. A dead battery is manageable. A dead battery with no one who remembers its chemistry is something else. Managed reproduction belongs in this system too. Births cannot be treated as a private matter alone when age balance, genetic health, and the timing of future workers affect everyone. That doesn't turn people into parts. It means the community must protect personal choice while planning for needs that stretch across generations. No single rule will fit every habitat or emergency. Education, then, is physical infrastructure. A classroom beside a workshop is doing the same job as a spare pump. One preserves a working machine, the other preserves the ability to build it again. The durable test arrives when those people can found a second independent habitat. It needs its own food, power, medical care, workshops, records and teachers. Until that happens, the whole society shares one chain of failure. And somewhere between the classroom and workshop, a child learns to cut a clean thread into metal. Nearby, a worn pump returns to service. Both repairs may take years to reveal their value. A settlement can look crowded and still be one accident away from ending. The hard test begins when you start taking important things away. Suppose the original ship is lost in a fire. Can the workshops replace its tools, or did the last precision equipment vanish with it? Suppose the main archive is corrupted. Do printed manuals, local copies, and trained memory carry enough knowledge forward? A library with one copy of everything isn't a backup. It's a very organized point of failure. Then remove a generation. Not gently, and not according to plan. An epidemic, an accident, or a series of bad years takes many of the original engineers and doctors. Can younger adults step into those roles? Have several people learned each critical trade? Can teachers train replacements without relying on someone who arrived from Earth? Managed reproduction belongs in the same practical test. The settlement must keep births, age groups, health, and genetic diversity within workable limits. A large headcount may help, but 5,000 people can still have the wrong age balance, thin medical skills, and only one person who understands the air system. That group can be more fragile than a smaller one built around overlap. The clearest test is simple. Can one inhabited node fail without taking everyone with it? That requires another habitat far enough away to escape the same fire, leak, impact, or power collapse. It must run its own life support systems and raise its own specialists. Yet the two places should still exchange people, parts, knowledge, and help. Independence doesn't mean isolation. It means neither home is merely an emergency room attached to the other. This isn't a test of whether two cultures have separated. They may share a language, laws, ceremonies, and a very active family group chat. The point is technical resilience. If one archive disappears, knowledge remains. If one crop fails, seed stock survives elsewhere. If one generation suffers terrible losses, trained successors keep the machines working. Headcount can tell you how many people are present under one set of assumptions. These losses reveal something harder. Maturity arrives when disaster stops being singular, when no ship, archive, habitat, or founding generation carries the entire human future alone. So the cleanest answer isn't a number of people. Any minimum head count depends on age, health, equipment, genetics, and how much bad luck arrives at once. Change those assumptions, and the number changes too. A stronger test is more practical. Can the settlement lose something important without losing its future? The old ship may still stand beside the new habitats. Its lights may remain on. Its computers may hold records, and its workshops may still make excellent parts. That's fine. The test is whether the ship has become helpful instead of necessary. Several kinds of backup must work together. Machines need spare machines, but they also need people who understand them. A factory needs raw material, tools, replacement parts, and technicians who can teach their replacements. A medical system needs supplies and trained staff. It also needs students who can become doctors after the first doctors are gone. Education is part of life support. So is managed reproduction. The settlement must raise healthy generations while protecting genetic diversity and allowing for illness, infertility, accidents, and ordinary human choice. A carefully balanced founding group may work on paper. As you might expect, real families rarely follow a spreadsheet. Specialists need overlap too. If only one person can repair the air system, one accident can threaten everyone. If several people can do the work, teach it, and rebuild the tools, an accident stays an accident. It doesn't become an ending. Industrial closure provides the materials. Teaching carries the skills through time. Redundancy gives both room to survive mistakes. Ship systems, factories, and schools are parts of the same answer. Eventually, the settlement should found another habitat of its own, Not another room joined by a cable, but a second place that can keep people alive after the first suffers a major failure. We can call the mission complete only when no inherited element remains indispensable. Not the ship, not its archive, not a sealed box of Earth-made parts, not the founding crew's private knowledge. The ship can stay. People can repair it, visit it, and remember it with affection. It simply no longer has to save everyone. That is technical independence. After all that distance, danger, work, and waiting, it may feel less like victory than the first ordinary night when nothing essential depends on a single thing. At the beginning, another sun in the windows meant the crossing was over. It was the first proof that the travelers had reached the right star. Years of darkness had given way to daylight from a sun no human being had ever lived beneath. Now the same view means something quieter. The original ship is still overhead. Perhaps you can see it cross the settlement sky as a moving point of light. Its tanks, computers, workshops, and stored records once carried nearly everything the settlers needed. For a long time, losing it would have turned a difficult life into an emergency. Then, slowly, that changes. A pump fails, and the replacement comes from a workshop below. A crop is lost, and another growing site has enough food to cover the gap. A doctor needs a tool that wasn't packed on Earth, so local machines make one. Children grow up knowing the ship as the place their parents arrived in, not as the machine keeping them alive. No single repair proves independence. Neither does the first local harvest, the first birth, or the first building made entirely from local material. The threshold appears across many ordinary days. More parts can be replaced, more skills are shared, food, power, medicine, and industry have backups. The population is large enough that one accident cannot erase an essential trade or an entire generation. This is where landing and arrival separate. A landing gives you a location. Arrival gives you a future there. It comes when the settlement can absorb loss without waiting for rescue from a world light years away. The ship may still be valuable. Earth may still send messages, designs, music, and advice. None of that makes the settlement incomplete. Independence doesn't require indifference. Earth can remain home in memory long after it stops being a lifeline. People may keep its calendars. They may tell stories about rain, oceans, crowded streets, and animals their children have never seen. They may celebrate old holidays under a sky where the seasons fall on different dates. Some will still call Earth home. Others will use that word for the valley outside their door. There's no fixed year when this change must happen. It may take generations. A settlement could become independent while still choosing close cultural ties with Earth. Another might need Earth's knowledge for centuries, even after it can meet its physical needs. Culture doesn't follow an engineering schedule. But we can describe the practical test in plain terms. If contact stops, can the people below continue? If the ship is lost, can they replace its remaining functions? If one habitat fails, are there enough other homes, tools, farms, and trained hands to keep that failure from becoming the end? When the answer becomes yes, the mission has reached its real destination. Not because every danger is gone. No human society has ever had that kind of safety. The settlers have simply crossed a boundary more important than the distance between stars. Their future no longer depends on one vessel, one habitat, or one supply chain reaching back to Earth. The ship can remain in orbit. It can become a laboratory, a warehouse, perhaps a museum. People below may still look up when it passes. They'll know that everyone in their world once depended on it. Then morning comes. Another sun fills the windows. Pumps start. Lights come on, breakfast grows warm, and people begin an ordinary day without needing anything from the ship above. Earth is still where their story began. It is no longer what keeps the story going.